Yeah.
Okay.
Thanks, folks.
All right, let's try this again. Now I've got this button. All right. So, God doesn't need a chemist was my mantra. I grew up I'm a PK, I'm a preacher's kid. And so I grew up in that family. In fact, my dad was a field artillery commander before he went to seminary. So I was probably about 9 years old when he went to seminary to about 11 when he graduated. So I was in it with him. And I grew up that way. And, as a PK, the congregation's always asking when you're going to do it. Right? And so my mother died at a young age, so I pretty much lack any compassion that there is at all. So if somebody comes to me and says, "Oh, Father Guido, I have this problem," and I'm like, "We all do, right? Grab yourself by the bootstraps. Let's get moving." Right? So anyway, that apparently is not a good criteria for the priesthood. So chemistry was an easy way for me to escape it. I figured I could separate my life from the church. My professional life, my personal life wouldn't have to be. God doesn't need a chemist, right? I also found at the end of my doctoral degree, when I was done, even though my wife and I attended church regularly, I really did not have to turn my life over to Christ at that point yet. And so I really felt like I was a self-made man at the end of my dissertation. That was actually the night that I was traveling back to Knoxville, the night after I defended my dissertation. And that's when God got a hold of me. And so I had to find a way forward to reconcile both chemistry and really rectify the metaphysical versus the physical, which is really what also was the dichotomy between chemistry is a very physical, natural process. And the metaphysical process. How do those commingle, and what do they mean, and what can I do to offer those services to God? So, this is what I do. I do a lot of talks. I do a lot of talks on the balance between science and faith. I do a lot of talks on Christ and culture. Cultures are another thing that is popular for me now. Being an academic, it's hard for me to separate culture because we live that every day with the students that we have and the diversity and everything that we have within my group and stuff. And so it's a really interesting place where we have an open environment in my lab where we can discuss any order. And I do it that way so that we're truth seeking. We're all full of soul sorrow and we're truth seeking. So those are the two things that we can all agree on in the lab, no matter what our alignments are. And so we discuss a lot of things, and sometimes we go over the cool beans and the discussions get weird. But Maxwell said in 1875, he remarked, "I think that men of science, as well as other men, need to learn from Christ. And I think that Christians whose mind are scientific are bound to study science, that this view of the glory of God may be extensive as their being is capable of." One of the things, I've never been shy about my faith at the university. Luckily, I'm in the state of Texas, so it affords me the opportunity to do such a thing. But I was faculty senate chair, and you would say to yourself, that is an odd position for a Christian to be in. But I will try to sort of emphasize what Maxwell is saying here too on the integrity side. A lot of times they put Christians in areas of government in the university because they have no integrity themselves. If you're always a self-made man in the university, how can you trust that person to trust your interests in the university? And so they're like, "Oh, well, let's just give it to a Christian. Right? He has integrity." But I think what Maxwell is saying here is somewhere similar along those lines, is not only that we appreciate the beauty and the order that we're going to see in the physical world, in the natural world, but we also have the integrity to produce, to represent it. We're truth seekers, true truth seekers. And I want to know if we're wrong. Absolutely, I want to know that too, right? I don't want to bury my head in the sand like ostrich if we're wrong. And so I think being a scientist like Maxwell, I felt it's a high Christian calling. So who else falls in this camp? Well, almost every father of science falls in this camp. And I introduced you to some of these folks because when we talk about some of these principles and how they work, I want you to know who came up with it. So Maxwell, we already talked about there, the reason evangelical Protestant. Michael Faraday was part of the Sandemanian Church. And so a lot of times you'll hear things about Michael Faraday that said that he was anti-church. The Sandemanians had this process. Okay? So you guys know about predestination and free will. Well, the Sandemanians had this problem where if you rejected the church, you were not allowed back in. So you couldn't flip-flop, right? You couldn't say, I'm a Christian, I reject it, and then I'm a Christian again. The Sandemanians said you were not welcome back. So Maxwell pushed against that. That was his debate against the church. So a lot of people will tell you, well, Maxwell was a Christian. Absolutely. I just gave you the quote from Maxwell. If he's not a Christian, I mean, that is the most beautiful quote ever. He just had a fight with Sandemanian church. So, Lavoisier, Boyle, Gibbs, which we're going to talk about because we have to talk about free energy. Free energy is a big problem in chemistry. We'll talk about microenvironments. We use all kinds of great terms. And then we have John Dalton. Now, he's my favorite because I'm a mass spectrometrist. And Dalton is the one that created the mass determination using mass spec, ion charge spec. So, and he's a Quaker. Francis Collins, we know Francis Collins, right? He just resigned as the head of the National Institute of Health. He was the father of the Genome Project. He is, let's see, we have an intelligent design group, and he's part of BioLogos, right, exactly. And BioLogos is interesting. I'm an Anglican, a conservative Anglican, and N.T. Wright has aligned himself with BioLogos. And so they both play guitar. Francis Collins is phenomenal. My uncle plays in a bluegrass band in Stanton, Virginia with his brother, with Francis's brother. And so, good guy. He also wrote The Language of God. And we'll talk a little bit about that. And then Thompson, I had to put him on there too because that's who designated the term in master charge. And so we have still our faculty members that still want to call that unit a Thompson. But let's give them Thompsons. Rutherford. So here's another good Anglican. I'll bring up all the good Anglicans, of course, right? So Rutherford was from New Zealand, won the Nobel Prize in the 20s. But his most famous discovery was actually in the 30s. He's the one who discovered the neutron. We couldn't rectify the masses of the atoms in chemistry up to that point with only protons and electrons. And as we were getting in the nuclear age, which was launching in, because we already had X-ray crystallography, we understand of nuclear chemistry, but we couldn't rectify the mass differences. And so we figured out that there's a subparticle in there that's called a neutron. And we're going to talk a little bit about weak forces too. So you need to know what that is. But Rutherford is the father. As a father of the table and the way that we look at it organized. It's not quite, we always show periodic tables like this. There's a couple of different options. A lot of times helium will actually be over here on the hydrogen side, because if you guys remember in the chemistry, it's going to be 2 electrons, but it's closed shell. So then sometimes you go there. So helium would be just as nice in the second column as it is in the last column. So you can do with that what you will. But other than that, most of those compounds. So what is chemistry and the age of the knowledge? So I covered that for you. So here's some definition, and you guys can just close your eyes. I'll give you some definition. We've got an atom. There's an atom up there, right? The single entity. It's made up of an electron outer shell, and the inner shell is made up of protons and neutrons. Protons and neutrons are going to be interesting because we'll talk about weak forces here in a moment.
So it's nothing smaller than those things.
There are bosons and quarks, which are the sort of the building blocks of it. It always takes a smaller particle to look at smaller particles. So technically, we can accelerate electrons to look atomistically, but below atomistically, we can only look at behavior. So we physically can't see it, but we can see it. And then I'm stepping in their realm. So I'm trying not to step in physics. So bosons and quarks, they own that, sort of. And we own the proton. But they are smaller, bosons and quarks. There was a book that came out called The God Particle, and that's essentially what they're coming down. What are the building blocks for that? And hopefully there in hope that based on those building blocks, they can explain why charge is positive, why charge is negative, why the neutron is neutral, and how you can swap between those. So, okay. And then we have a molecule. So there's a molecule on that side there, just do a simple one. Then we have an amino acid. Amino acid up here is a molecule with a certain set of structures. Its backbone is the same for every amino acid. Its side group is different. Okay? And so it builds a protein. I will get my protons and proteins mixed up. It builds a protein, and here's a small peptide that has a series of amino acids on it. So it's larger. And then we have nucleic acids down here, right here. And when we build those, they build up DNA and RNA. And you can see that even when I do a very simple structure in Avogadro, it goes ahead and builds an alpha helical structure. Right? And so that's in tune in nature. So let me tell you one other thing about chemistry on this planet. It's left-handed. So it's kind of a big joke. I think God's joke on all of us, because we call right-handed rectus, which means right, and we call left-handed sinister, which is S. And so we do that because, you know, we're so smart back in the day. But if you're writing with your left hand, it's Satan and smack into your right. Well, then it's really funny that when we actually learn chemistry, all the chemistry in the body that's pharmacological and active is typically left-handed. We very rarely have a right-handed molecule. That's not tox. Yeah.
What do you mean by right-handed?
So if I take this group, this molecule, and I rotate it with my thumb up like this in that direction, it's a right-handed molecule. If it was going the other way, and I rotate it with my thumb out this way, it'd be left-handed. So it's just called chirality. And some molecules have mirror images of themselves, and the mirror image would be one way right-handed. And it's just typically everything's left-handed. That's going to be important in a moment too. Because if things happen in random processes, you're asking question, I'm flipping quarters, right? Then how many of my compounds on this planet will be right-handed? And how many of your compounds will be left-handed? You would think 50-50, but almost every time we flip a quarter, it ends up being 51-49. But it falls one way or another. So it's really close, right? So that's right. Depends on if we toss it an even number of times. So let's start with the Big Bang. I want to start with the Big Bang. This is going in the physics world, but the Big Bang is where chemistry came from. Actually, chemistry didn't really start in the Big Bang until I think like 10 to the minus 43 seconds, something like that, within the expansion. One of the things that I want to give you this on the Big Bang, I've talked to you guys about the Big Bang before, and how this is kind of a paradigm shift. We had an infinitely old universe, and it changed to a cause. Right? An event cause. Okay, what do we call that event, that cause at the very beginning? We call that a singularity. Mathematical terms, it's a point at which a given mathematical object is not defined or not well behaved. I put abiogenesis on there for a moment too, because it's a singularity also. So don't be confused by the science. I use big words. I have this word, it's called lyophilized. Okay. And I lyophilize things, and that sounds really important. That means freeze dry, right? So if you go to Bass Pro, you can buy your own freeze dry, right? But I say lyophilize, and that makes me sound real smart. But all it is freeze dry. So I say singularity to you, and what does that mean? Well, it means a single event occurred that I can't prove, define, right? I know the event occurred. I can see that. And if you, at some point, I'll give that talk again. If we want to talk about Big Bang again, we can do it. But It's a singularity. So always be careful with that because people will use this term often and that's great. But it typically means that prior to the singularity, we don't have any proof of that event. And since we don't have any proof of that event, we need to be wary of it because then the question is it science? Whatever I do before that singularity event, is it science? Can I reproduce it? I mean, I can do mathematical models for multiverse, no problem with that, right? String theory will do that for me, but I can't prove it. It will remain theoretical. So abiogenesis is the same way, and I'll tell you why. This is a chemical problem. This is the physicists have to deal with that problem. I have to deal with abiogenesis. Why? It's not a biological problem. I'm sorry, I don't want to insult any biologists, but it's not a biological. It's a chemical problem. Why? Because we have an inorganic Earth. We know that. When the universe was formed and the Earth was formed, it was literally formless and void. I mean, it wasn't really formless, but it was without life and without the building blocks for life. Most of it is an iron core. We have carbon. Carbon came in the form of our atmosphere. We'll talk a little bit about that. Standing in our latest experiment. Questionable. But there are a lot of experiments that go about creating life. Now, it's kind of nice that we are organic chemists. We have organic chemists, so we know the cookbook. So if I want to make an amino acid, I can go make it. It doesn't make me God. It makes me have to prove that that process occurred in some way, similar to the way that I'm creating it. And that's a difficult metaphysical problem because why? I'm an intelligent being, and an intelligent being created this method to create an amino acid. Which begs the question, can an intelligent being do such a thing? Or can we do it based on random processes? And so I'm just talking about designer versus random processes, really what I'm going to talk about, because those are the two designations that we can really do from the fine-tuning argument and the natural causes. So abiogenesis. So we'll talk about that a little bit. So here's Big Bang. I just put that up here because it's always very interesting to see when chemistry actually exists. And sorry, I think it's 10 to the minus 6 seconds. So when the Big Bang occurred, it's amazing to see space-time change. And we talked about that before, and you can ask these guys about space-time. But it's a space-time bubble. It started small, the time is small, expanded. Now we're up to here, and chemistry was created very early. Weak forces and strong forces for nuclear forces, electromagnetic forces were established very quickly in the universe. And those values had to be nailed. Because if you were off a little bit by any of those values, you would either have a universe full of protons only, a universe full of heavy, or nothing, because nothing could come together. And I'll show you the statistics on that. The fine-tuning argument is not owned by religious, metaphysical, faith-loving people. This is owned by sensible people, rational people, atheists. The fine-tuning argument is a great argument because it's very difficult to say. We know that if any of these numbers would change, it wouldn't exist. And now we have, the only way to explain that away is to go with the multiverse, right? A whole bunch of Big Bangs occurred. Infinite number of Big Bangs occurred. And somewhere along that, the perfect fine-tuning came. That's great. That's your religious statement. Mine, I call him God, and he loves me. Does your universe love you? Your multiverse love you? I don't know. I think it does it. Yeah. Okay. So what are the fine-tuning arguments? The fine-tuning arguments were built initially in physics, and they were built around those first 5 cosmological constants, not, but the first 4 were the gravitational force, which chemists don't care about. They don't care about gravity. Gravity only works when you have a large mass of chemistry, a really large mass of chemistry. Electromagnetic forces we care about. We care about strong nuclear forces, and we care about weak nuclear forces. The weak nuclear forces I told you on that was how the protons and the neutrons stay together. right? Because if there's nothing, here's an electron here, there's a proton here, what keeps that electron from collapsing in, what keeps that proton from ripping out, is this balance of these forces. And then, of course, we know the electromagnetic forces. Those are ones that are really dictated by the electron. And in chemistry, the electron is king. Protons, lovely, but the electron does all the bonding, does all the everything that we care about in the strong nuclear forces. So I'll go on. There are other ones, and I highlighted the ones that are chemically related because this is a chemistry talk. So initial distribution of mass energy is one, ratio of masses of protons to electron, velocity of light, max excesses of neutrons over protons, and then on and on. Proper concentration of sulfur, I have no idea why that is a fine-tuning argument. I'm going to have to go read a little more on that. I hate sulfur. It's terrible, it smells bad. But for some reason or another, we have to have the right concentration of that. I mean, Venus has a lot, and clearly it's a dead planet. So, and the polarity of water molecules. Water is the craziest chemical molecule that you can think of. It has very, very unique properties. It's the major solvent of the world, right? It's water. And water freezes from the top down. And nothing else does that. They freeze from the bottom up. And we could not have life on this planet if water didn't act that way. Why? Because plant life on the bottom of the oceans would be dead. Then the surface of the oceans would be dead. And so we have this unique molecular force, water. It sits on one extreme. We call that hydrophilic or lipophobic. So water loving, fat hating. And then on the other extreme, we have chloroform. And chloroform is fat loving, water hating. So the extreme solvents of the world. You can go even further if you want hexane, oil and gas. Okay, so if you want to know all of them, now, if you just did something, so Gil Gazamas, who wrote The Privileged Planet, said, if you just take these and just do it as a power of 2 odds that occurred, you would still have reached 10 to the 22, in which that's the same number of stars in the universe at the time. I think now we've increased that. But at the time it was written, there were 10 to the 22 stars. Universe. Okay. So here's that fine-tuning argument, and here are the stats. So we have gravity, electromagnetism, strong nuclear force, weak nuclear force, and principle of quantization. And we'll talk about quantization in a moment. But if we just start taking these deviations, 1 times 10 to the 37, 1 times 10 to the 40, 1 times 10 to the 55, 1 times 10 to the 59, these numbers become so large. These are numbers that we can't even think of. That statistically, it's very difficult to say that the universe wasn't fine-tuned, that there were parameters that existed in order for all of these forces to occur.
Which one represents gravity?
Gravity is the
Electron, proton.
ratio of electromagnetic force to gravity. It's the second one, it's in the fourth. We still don't understand gravity. Gravity's a tough one. I mean, people say we do it all the time. Newton came up with the equation. Well, of course we can. We understand it that way. We don't understand it on the fundamental force yet. It's not that I don't think we will. And if we do, it's not going to unvalidate God. You know, that's crazy. So just even in a brief history of time, Stephen Hawking has a nice quote about this. And I actually got to see him in person. That was another highlight of when we came to Texas A&M and gave a talk. When I say a talk, he hit record, he hit play, but it was brilliant. He was there. There's a little anecdotal story about him. You know, he speaks like an American, right? But he's a Brit. His little computer. And so the guy who created this computer for him was an American. And so he recorded it in his voice. And Stephen Hawking was given this device and he used it for a while. And people have noticed, hey, doesn't have a British accent. And Stephen Hawking says, doesn't care. This is a So a miracle of invention at the time. And he was just super happy to have an American accent. So he kept the American accent the whole time. But the law of science, as we know them at present, contain many fundamental numbers like the size of the electric charge of the electron and the ratio of the mass of the proton and the electron. The remarkable fact is that the values of these numbers seem to have been finally adjusted to make possible the development of life. And so we're still looking for the machine that adjusted these parameters. Okay, so now where did life come from? So here's our next singularity that we have to deal with after the formation of the chemistry. Now we have to deal with abiogenesis. And abiogenesis is a problem. Evolution tends to not be a problem because you can see microevolution on a scale all the time. But the big problem is, where did this tuning come from in the biological world? And it has to start with a non-organic chemistry planet and creating organic chemistry, right? Now, you can fall into the group of that it was planted here, but then you just push the problem to another planet. So, you know, yes, we have actually had a volcanic eruption that occurred on Mars and debris hit the Earth. But it actually made it less life, because now we have that amount of rock that has no life in it at all on our planet. But there are people that say that you could have some sort of form an object from another galaxy or from another planet that seeded the chemistry that was necessary to start it. But once again, I can put anything up front I want. Why? Because I know how organic chemistry works now. So I can take all the building blocks that I want as fundamentally as I want to and create the chemistry I want to, because I'm now intelligent enough to do that. We've seen these plumes down where lots of cyanide come out. So that's carbon nitrogen that comes out of these plumes, and there's life there. Cyanobacteria grows there. That bright green bacteria that grows in the presence of these high streams of cyanide and sulfur. And then I drew this picture here because there are people that believe that alien life in planet. So if you haven't seen the movie Prometheus, just don't watch the whole thing. Just watch the first 5 minutes. It'll explain how life got on this planet, and you'll be fine. Right? It's came from another world. So we can have any of those ways, but we don't want to push the argument away. So we try to figure out what's going on in here. One of the ways Stanley Miller did the experiment, where at the time we believed there was a lot of methane in our atmosphere. Now we have to have a carbon source. We have to have a good carbon source, and methane is organic. It's an organic molecule. So we need that there. So it's convenient that we have the building block of organic chemistry in there. Now, is that unheard of? The moons around Jupiter and Saturn, some of them have seeds of methane. So those common small molecules do exist on other planets that you could use to seed that reaction. But as we all need, we need water as a solvent, right? And so having a lake, a planet that's a lake of nothing but methane is somewhat problematic, because you're not giving it any foundation to grow with. But we won't argue that now. So at the time, it was water, methane, ammonia, which is a nitrogen source, and H2. And what Stanley Miller did was he put a lightning spark in there. So if he says this is in the atmosphere, and we have this lightning spark that occurs, what molecules are being created in that environment? Now, we'll talk about entropy in a moment, but we can subside entropy if we can overcome it by putting enough energy into the reaction to cause a reaction to move forward. So we can do that and overcome entropy if there's enough energy. We'll argue about that one in a moment, but let's say that that's the case. And these are the building blocks of it. He actually created quite a bit of glycine. And a couple other, I think it was 6 amino acids total in this mix, which is great. You have amino acids. And they self-assemble how? I mean, now I have, so Stanley Miller's experiment has actually been sitting on the counter. It's a closed system. And every now and then they sample it. No, you can't sample it. You know what I mean? Yeah, that's right. We all have that problem. Yeah, and so he has a sampling probe. So you try to make it unidirectional so that you don't add any chemistry back. Doing this experiment on planet Earth is problematic anyway, because you have to prove to me that the scale to start with. But we won't argue that. We'll take Stanley Miller at his word. And they tested it later. And they found out that there were actually more amino acids there than they thought from the beginning. None of them self-assembled. I mean, none of them started to connect together. And if they have to connect together, they have to connect together in a random way that is biologically active. But then we'll have another problem. And the problem is DNA and RNA. Because, and I'm going to show you the video in a moment. So it's the most lovely video I've seen on there. And just a beautiful way to explain how proteins and DNA and RNA work. But they work together. And it's very difficult. Most scientists today fall on the fact that RNA has to be the one that is created first, not the protein. But it's hard to say. In every living organism that we have on the planet, they coexist. Both do. We can't find one organism that has one without the other. Now we have prions, and prions just attack the body. They're proteins that are folded incorrectly that cause an immune response. Yes, but they don't live. And so is this a language? Yeah, right? Because when we talk about languages like computer languages, we're talking about a binary system. When we're talking about DNA, we're talking about a quaternary system. Quaternary system of 4 things that can language everything. It looks like there's a coder, right? Somebody who coded this so that, and very interesting things are coming out of science today that again support the design movement. I don't want to say intelligent design. I stay away from that, not because I'm a full believer in intelligent design. It's just, it puts me in a camp. It's weird how these words work, right? And so I have to say things like designer, so that, because biologos, okay, and then ID, okay. So, you know, I try not to stuff myself way far down the camp trail that I politically aligned myself, right? But I do love the ID movement, by the way. But it looks like a coder. So how does it look like that? Well, here's the code. We have TAGC, and that's for DNA. And DNA will then form connections to the ATGC, that's AGTC, in each one of those wheels. So you can go down, you see what I'm doing? I can go down the AG path, or I can go down the AGGA path, right? So it's the combination of up to the 3 powers of everything that can be done with the 4 system, right? Does that make sense? Yeah, so these are, you remember doing that in there. You got 4 things on it. How can you put them over there? So this is the total number. Well, guess what they do? They code for 20 amino acids. 3 of the letters together, GAG, code for arginine. Okay. And right, and ATC for asparagine, and AGA for lysine. Those are all just amino acids. So we have the code that converts the DNA RNA to the amino acid that's associated with, so that an RNA can come out and build the protein that the body needs. Still haven't answered the question, when does it need it? How does it know where it needs it? And why does it only cut that one section to make that protein? Transportation in the cell, it's a biological problem and a physical problem. It's where physics and biology can come and figure it out. Chemists don't have an room there, but somehow that has to be figured out. back in the day, we used to say diffusion. Well, if diffusion was the process for life, it wouldn't occur very rapidly. It would be really slow, even slower than it is now. So it's amazing that it does. So there's communication network that's occurring in the cell that tells them what RNA piece I want to build what protein I want that folds a certain way and acts a certain way. I'm sorry, it looks like a code. I just can't imagine, I can't fathom my mind around it. So let's watch it. Okay, hold on one second, because I got to get everybody in Zoom land. Can you see the video, Jason? No? Oh, you can't see the video. Okay, good.
Yeah, I can see it.
Here is a cell, the basic unit of all living tissue. In most human cells, there is a structure called the nucleus.
It's only 2 minutes. So.
The nucleus contains the genome.
Oh,
In humans, the genome is split between 23 pairs.
sorry, they can't see it. Now can you see the video, Jason? Oh, shit. All right, that's okay. Let's stop share. And then we'll share. And then we'll share this video right here. Now can you see it?
Yes.
Got it. Good.
Of chromosomes. Each chromosome contains a long strand of DNA,
This is,
tightly packaged around
Whoa.
proteins called histones.
but it gets exciting here.
Within the DNA are sections called genes. These genes contain the instructions for making proteins. When a gene is switched on, an enzyme called RNA polymerase attaches to the start.
When a gene switches on, that's a scientific term, right? Okay, when a gene switches on. So that's the biological term for when a gene switches on, Jason Brogdon.
Onto the gene. It moves along the DNA, making a strand of messenger RNA out of free bases in the nucleus.
So that part there is an enzyme. And an enzyme is just a protein. A protein, an active protein. So the enzyme, the RNA is going in there. It's essentially the beautiful thing about the alpha helical structure, right? Again, everything left-handed, is that when it goes into the protein, it opens it up. And because it's alpha helical structure, it's like almost like Chinese finger cuffs. You can open it up and then it just closes back on the other side. So only the part in the middle that the enzyme has is open and they can transcribe it. Right, so you see, that's amazing.
DNA code determines the order in which the free bases are added to the messenger RNA. This process is called transcription. Before the messenger RNA can be used as a template for the production of proteins, it needs to be processed. This involves removing and adding sections of RNA. The messenger RNA then moves out of the nucleus into the cytoplasm.
Yeah, by magic.
Protein factories in the cytoplasm, called ribosomes, bind to the messenger RNA. The ribosome reads the code in the messenger RNA to produce a chain made up of amino acids.
And so
There are
there's
20 different types of
the
amino
three
acids.
matches at the bottom that you saw.
Transfer RNA molecules carry the amino acids to the ribosome. The messenger RNA is read 3 bases at a time. As each triplet is read, a transfer RNA delivers the corresponding amino acid. This is added to a growing chain of amino acids. Once the last amino acid has been added, the chain folds into a complex 3D shape to form the protein.
All right. Right. So that's that process. That's the process that randomness delivered to us. Pretty amazing. What do you see now?
That, yeah, I've seen the video of it.
You see?
The only purpose is that now to the PowerPoint. Yes.
Yes, good. All right. So in that process, there's a great book. It's called Evolution 2.0. Perry Marshall wrote it. I mean, it's a great book. There's some problems. If you're a young earther, he's not friendly. And when I mean not friendly, I mean he's vitriol. So he doesn't act in a Christian behavior. He acts as an intelligent design advocate only, and not bringing the metaphysical faith part with it. So he starts off really very rough on it. So if you can get past that, and I'm not putting God in a box. So, but once he's past that, he gives you all of the switchblade knives of how we know DNA and RNA work in an actual form, not random at all. And so these are called, there's transposition, which is the movement of DNA from one location to another that occurs. There's horizontal gene transfer, the movement of genetic information between organisms. There's symbiogenesis, with two different organisms merged to become a new one. There's epigenetics, real-time appropriate adaptations to the environment, brown eyes, dark skin, these types of things that are adapted for the environment that we're growing up in because we have to overcome. Epigenetics. This is what we typically would call things like microevolution, evolutionary form. And then gene duplication, more than one copy of a specific. So this is growing every day. So in biology 1, you learn about random mutation, random. And then your senior genetics class, you're like, no, none of it's random. It's all prescribed, and these are the prescriptions. These are how it works. And we still don't know how microorganisms work with us in our microenvironment, but they work through epigenetics, because we know things like if I go and drink water in another place, I'm going to get sick as a dog because my body can't adapt to that microenvironment, but other people can. And what does that do to my genes? It's amazing, right? Junk DNA is another thing that's a throwaway. They say something like 90-something% of junk DNA. Well, that's fun, because now CNE News tells me that junk DNA is not so junky. And Nature tells me that we're rethinking junk DNA. And then here's an example of mutation within junk DNA linked to autism disorders. So here what we're saying in the middle now is this middle junk DNA, sections of DNA around and between genes seem to do nothing, and we're called junk DNA. But now researchers think that junk DNA contains a large number of tiny genetic switches controlling how genes function within a cell. That's 90% of it that we called junk 5 years ago. So today we're saying it's active. And so we have a problem. We don't have a problem. It's great for us. I love abiogenesis. I love Big Bang. I love all that stuff because it's just pointing them up to a creator. And I can't imagine a creator that creates that doesn't love me. So that narrows the field down a little bit. So real quick, we'll end this up with Gibbs free energy to really bore you. So here's Gibbs free energy, delta G. Free energy essentially says that if delta G is less than 0, the reaction will occur spontaneously. Okay. If it's greater than 0, then it has to be pushed. You have to add energy to the system in order to do that. These reactions I've shown you all require energy. They all require energy to go into. I'm an organic chemist. I put it on a pot. I can't just mix a bunch of chemicals in there. That's what nutraceuticals are. And when did a nutraceutical make something else? It doesn't. It's just a bunch of stuff stuck together. I have to put energy into that system and control that system from one wave to another in order to create the molecule complexity that you're seeing right now. So that's entropy. But we're going to talk about this S one, entropy. Entropy says any type of spontaneous reaction is going to go to higher disorder. Now, not necessarily, because enthalpy can overcome entropy, right? And I can still have a spontaneous reaction occur. like, reaction that goes down a well. I don't know if you've ever seen this, but you got two molecules that are coming together, and then it's got a lower energy connection. So that would be where enthalpy rules. Entropy doesn't rule. But entropy as a positive term makes delta G spontaneous, right? So there's the equation. Here's NASA. You go to NASA's website. If you want to know about the second law of thermodynamics, it's right for you. Here's a heated system. Here's a cold system. And essentially, it's going to say that when I open up that system in that tube, that the closed system will have to equilibrate, and it'll equilibrate to higher disorder. And so as my system starts to expand, the order becomes higher. So we'll go back to Big Bang. We have an expanding space-time. And Hubble has now proven that it's a problem. That's a problem because enthalpy will win. So how do we get a highly ordered planet? I'll tell you. Singularity. And that singularity is called, the term I will use, microenvironment. So I love this term because I was down in the Antarctic region, and the Antarctic's getting colder while the Arctic is getting warmer. And so they were trying to explain to this couple of philosophers down there, telling me what that was. And I said, well, it's colder down here. And they said, only in the microenvironment. No, you don't know how thermodynamics work. It's colder in Antarctica. The sum total of it all is colder. It's not the microenvironment is warmer here, and that suddenly makes the colder part go away. Same thing here. The microenvironment is our sun. It's perfect. And the orderness is perfect. That has to be a microenvironment that's controlled by enthalpy and not entropy. And that means heat has to come in and do this reaction. And that's hard to explain, right? So entropy is a problem. There's entropy, goes away. It's like saying, okay, on a closed system, here's the bomb. So, here's the nuclear explosion. And when that nuclear explosion is ordered, this is what it looks like. Right? So I blow up a nuclear bomb and it falls down and creates the city. Right? We all think rationally that that's going to occur instead of that, because that's what occurred when the nuclear bomb went off. And statistically, I would say it would not look the same every time I did that explosion, but it would look close to that and not close to that. Okay. And then quick and chemical, the eclipse. This is part of Gil Gazamas's argument that if we are unique, if we are alone, then there ought to be things that point to discovery, that we have the ability to discover our universe. And chemically was the makeup of stars for us. And our moon exactly eclipses the sun. And because that event, does that event have to occur for life to be on Earth? Absolutely not. It just happens that it does. What are the physical odds of that? But let's say, okay, we're just living the physical odds of it exactly eclipsing the sun. But because of that event, we can solve Einstein's gravitational force constant to 7 decimal places. And we know the chemical makeup of our sun. Because what happens is that's what the electromagnetic spectrum looks like when we look at our sun. But as the eclipse is occurring, we actually start to see the lines of hydrogen and helium, calcium, and iron. Is that right? That's that right? Yeah. That make up our sun. So biblical support for chemistry. I had to dig on these, but these are fun because there's not a lot of chemistry in scripture, but I made it fun. So you ready for this? So Jeremiah 2:22, although you wash yourself with lye and use much soap, the stain of your guilt is before me. So that describes the first surfactant, right? So you know what surfactant is? It's both fat loving and water loving, so that you can get. But apparently that stain can't even get that. I mean, a solvent that's perfect fat loving, water loving can't get that stain. And Proverbs 25:20, like one who takes off a garment on a cold day, or like vinegar on soda. How many of us did the volcanic reaction in science fair when we were in 6th grade? Is one who sings songs about a troubled heart, right? So here's the reaction. There's acetic acid, baking soda, carbon dioxide, water, and sodium acetate, and it expands quite rapidly. So you can see that even then, during the time when they mix those two together, that they got this one who takes off a garment on a cold day, the absurdity of it, right? This is my favorite. So now we have Isaiah 33:10. Now I will rise, said the Lord. Now I will be exalted. Now I will be lifted up. You have conceived chaff. You will give birth to stubble. My breath will consume you like a fire. The people will be burned to lime. That is chemical. Burned to lime. A person is chemical. Lime is a product of that chemistry. Okay, can that be done? I had to create the reaction myself because apparently nobody went down that path. But I did it. So bone is hydroxyapatite. It's calcium, phosphorus, oxygen, hydrogen. And if I add a small amount of phosphoric acid, only small, because it'll form the calcium hydrogen phosphate plus water. But then the second reaction, that one plus water will give me calcium oxide plus my phosphoric acid back. So now it's in the environment, I can feed it back to the reaction, right? So that reaction is perpetual. And so, but in order to form lime, I need CO2. So what do? I burn fat, right? So there's a fatty acid there, C55, plus 78 oxygens from the atmosphere. And it produces carbon dioxide and water. And that carbon dioxide feeds the reaction. And thus, burning somebody creates lime. So there you go. The Bible is statistically, I guess, right?
Is that a stumping nature?
It's not. It needs heat. So, but that's great because they're burning the body. So I don't know that Fahrenheit 451 would be enough to sustain the reaction. But anyway, it was fun to create it. And then there's the salt. When does salt lose its saltiness? It doesn't. So this is an extreme event. The only time it will even occur on our planet is if rainwater gets into the salt and it forms another salt, like sodium sulfate or something like that. And then the saltiness will lose its saltiness. But I put that up. And this last slide is what is the best chemical miracle in Scripture? Water in the wine. That's right. All the rest are physical. Walking on water, that's physical. But water in the wine is amazing because in it, he had to bring atoms into it. Because if it is just water to wine, water is only H2O. Wine requires sulfur, nitrogen, congeners, tannins, all kinds of stuff. If it's the best wine they ever tasted, it had to have been aged in a barrel for 20 years. You know, all kinds of nutty stuff. So that's quite a chemical miracle. It's really the only miracle I can see up there that's chemical. But so it's got, I mean, besides rising from the dead. Yeah, that's biological. Walking on water is physical, but anyway, that's it. I know it went a little long, but I appreciate you guys' attention.
Based on that previous diagram showing how to turn somebody into lime, I'm going to stay on your good side from here forward. I've seen some TV shows about guys that do that.
I bet your lime is definitely a product. There's no doubt because, like I said, I mean, you still have hydroxyapatite and you have fat. Yeah, it's gonna, there'll be lime there.
Questions, comments? Dr. Verbeck. Let me start out because you guys are all shy. But I know Kyle's got at least one or two, maybe both and two. How do you deal with the multiverse objection to all of this?
Yeah, I mean,
and maybe you could explain that. Probably some know it, but you could explain what that theory is.
Sure. And so in science, we have to be, more Aristotelian with the definition of what we're talking about in science, because it's typically something we can either prove in the lab, or we can prove processes that lead to the same sort of results, right? Which is what we're trying to do with the abiogenesis. We're just not having a lot of success with it. So that being said, I normally frame science in the realm of science and say, well, the rules of science are that they're observable and they're reproducible, and that these any pre-singularity events that can't be done in the lab is a faith statement, right? You have to believe that. And as an analytical chemist, I challenge my students all the time to take my analytical core class. There's a difference between believing me and knowing it, right? This is actually a Thomas Aquinas quote. He actually said that that believing and knowing, you can't know, you can't believe.
You can't know something.
You can't know something if you believe it, and you can't believe something if you know it. I disagree with that, but it has a good context in this, in that any of that where you put your faith in theory, I quote Feynman. So Feynman says, it doesn't matter how good your theory is or how smart you are. If it doesn't agree with experiment, it's wrong. And so I usually go to that.
Yeah.
And
So multiverse doesn't have any.
string theory is a theory.
Okay.
Yeah, and they poke holes in string theory all the time, but yeah, and you would have to have some observables in our universe that there are more than one universe. Well, a lot of times we also use the argument of multiverses would have to be almost an infinite process, and then I go in the infinity is absurd argument that I've used before, and describe to them how infinity is a construct and can't be a thing. And so,
Okay, thank you.
yeah.
And I just want to make an observation that on one of your earlier slides, you showed the probability that those constants were fine-tuned. And one was like 10 to the 100th power. My understanding is 10 to the 80th is all the atoms in the universe.
Yeah,
Around there.
that's right.
Around there. So these seem to be so, so minuscule in terms of the odds. How could anybody deny? Right?
Most of it is the lack of knowledge and ignorance. You see, well, how many biologists in this room? Raise your hand. Yeah, you are. Oh, that's right, because you walked the line between and my. Yeah, so you're both. You messed up my whole argument.
Yeah, I was going to say actually, for at least a decade, the teachers have been teaching that junk DNA is misnamed.
Yes. Oh, that they believe that it was misnamed from.
Right. Yeah, and of course they made a big deal about how it was called junk DNA inappropriately. So I don't. It's been more than 5 years. Is my point.
Oh, okay. I'm sure. Yeah. That. I mean, we knew about transposition in the corn. I mean, 50 years ago, right? So, but yeah, I'm talking overall on the masses of what the masses think. Sort of the media feed into what.
You pick the name and you teach now it was misnamed, but you don't change the name.
Right. That's right. That's right. Well, mainly probably because we don't know what its function is quite yet, but overall you'll find that this is true at UNT, and I'm saying it anecdotally, but you'll find that mathematicians and physicists and some chemists are more faithful, and then it starts to slide away the more you get towards biology and social sciences. Not that biology and social science, I'm not saying that. Because I'm a biochemist, and so we sort of walk the line, but it's people that see the order in things tend to be faithful, and people who don't see the order in things tend to be unfaithful. So, and that has to be because random mutations have to supplant a designed creative environment. It has to supplant it. There's no option in between. So.
I'm going to make a call up. Could you just call to TJ and Jacob if they have any questions on Zoom?
Oh, TJ and Jacob, do you have any questions?
Open up your microphone if you do. Okay, probably not.
I think they're all gone.
No, they're still there. They're still
Oh, okay.
They should. Anyone else have any questions here, Emma?
How would you respond to the double argument? Like, I can guess what you'd say, but I want to, like, it's been a while since I've done that, so.
Which argument?
You're talking about the soup?
No, so like the fine tuning, like counter argument, like, oh, okay, well, a puddle lands in like a pothole and it is a certain shape,